that.
Okay, so we're gonna actually start doing an application of this today. There's one spot, I'm not gonna do a derivation for you, and it's an important derivation because we don't have the mathematics for it. I'll set it up and I'll tell you what the result is, and then kind of show you how the result goes, because we're gonna use it in for this temperature dependent constraint theory. So let me put them forward here. So we went through a calculation of plausibility argument for atom gives. And what does this end up equaling?
Infinite viscosity
Or infinite temperature viscosity
times the
B to the B, which is some constant connected somehow with energy. Okay. Over JBT.
There's definitely configurational entropy.
And then the configurational entropy per atom. And what we did is per unit particles in the system. So we took the log base 10 of this. Okay, and that's what we had.
Can I question your mathematics here a little bit?
There's some factors in it that we're not going to worry about. Yes,
Okay.
but we're not going to.
Is it?
Okay, there's going to be factors, and what do the factors do? B. Okay.
I didn't see.
Yeah, so that's no, it's completely. Okay, and also it's going to be written up as a whole set to actually put the correct factors.
Okay.
But yeah, if you look at that one, Ellen, I believe log base 10. I don't think so.
Yeah.
That's fine. We're not going to about that right now. Because again, because of the, we can dump things.
Yeah, sure. You can do the fraction rule.
Yep. And so what are we going to do here? We're going to look at families of glasses. So we can look at, for instance, we're going to look at a couple of these. Well, one today. If you look at this one here. Look at that one, you can look at other ones here. And so this eta here is going to depend in your and configurational entropy particles. They're going to depend on the position. They're going to depend on the composition X. So I could just as well write this here. Log base 10 here. It's going to be this eta as a function of X. And it's also a function of the temperature as well. Here, this guy here. This is the same for everything, so we don't have to worry about that one. Plus this B of X. Maybe this T here, here, and this has to C of X. And this can also depend on T. Okay, so we said that's fine and good, but I want to do two different compositional values here. And we said one of the compositional values we're going to call what? Reference. X of R is a reference. So what I can do is I can actually then write this as I can put an R here. So I can write the whole thing here then with an R.
That's pretty low. So you're making a claim that B does not depend on temperature?
Yeah. And that's consistent with the derivation that I gave you. Now you could argue that whether that's true or not, that's fine. But again, remember the assumption we made about that law.
Yes, okay, sure.
So XR is the X of R refers to some reference composition. Now, how could we equate them? We said, oh, I know that if the temperature is
Glass transition.
the glass transition temperature, then what do we know about all glass transition temperatures? The log of the glass, the log base 10 of eta at the glass transition temperature, no matter what the composition has to be 12. So we said at T equals Tg, independent of the temperature composition. X must have log 10 eta So what does that mean here? That means that these are gonna be the same, these are gonna be the same, and then at the glass transition temperature, this has to be the same. So what that allowed us to do is to say that this Bx over KB T glass. And this T glass here might actually depend on the composition. Maybe it does, maybe it doesn't, we don't know. It might change.
Usually does.
Okay. Here. Then has to be then this BXR, KB, TG, XR, S sub C, XR, TG, XR like that. Maybe it's canceled. Woohoo! Okay, and then I can solve then for the glass transition temperature semi-composition X compared to some reference temperature. Glass transition temperature at some reference temperature. Equals then what? Equals then this EX over BXR. And then we have this SC XR PGXR S sub C X each of X. Then we made one claim here. Oh, most make that make a lot of claims, but that's okay. What do we assume about that?
That is about the same.
That's the slowly varying function of X, so that's going to be approximately 1. So we're going to say that P of X is a slowly varying function of slowly varying function of X. And again, this is within the same glass family. Okay, within a glass family. So in other words, we're not comparing a foul fake glass to a fake glass. We're not doing that. It's all going to be the same family glass. A slowly varying function of X within a glass family. So what that gave us was the principal equation. This is TG max, TG compared to reference temperature. Again, it's presumably we know what this is. Because then it's going to be approximately then how the same. It's really approximate. That makes sense? That's what we have. Questions of that? Okay, so now let's see how we're going to then tie this into the floppiness and stuff like this. Okay, so this is going to be the workout, and I brought the paper to get the first thing. Let's roll over. Let's have this start with resolve. Okay, so this is Geraldo. Now let's go from. Again, really, really bright guy. He's a theoretical physicist, as I said, from Mexico City, and he just an extremely nice guy, very, very smart. And I refereed one of his papers, which actually made use of a simple model. This one makes use of a simple model. So therefore, based on 2 data points, I can include that in all of his research. Clearly, he uses simple models and produces profound results. Okay, clearly based on the 2 data points, that must be the case. Okay. Now, what did he do? So he's going to take a system. He's going to take some system, and what he's going to do is he's going to switch into what are called normal mode coordinates. Don't worry about too much about what that means. But what he's going to look at, he's going to say, let's assume that this system here can be modeled as a collection of harmonic oscillators. Okay. So model a system as a collection of harmonic oscillators.
So many assumptions, it's hurting my brain. They're like clearly not true.
Okay, I think everything's harmonic oscillator.
Okay.
I can't think of any system that isn't.
Did you comment?
Well, I think everything's a perfect harmonic oscillator. I don't know how cannot. And so, if what would be then the energy then for this? And again, that actually assumption is actually very good if,
You're at 0 Kelvin.
well, if you're actually not too far from the minimums. Because no matter how complicated the potential energy is, you can always basically, if you're near the minimum, you always have basically something acting as a harmonic oscillator. Okay, so that assumption isn't as egregious as you think. Okay.
Yeah.
So what are we gonna have then? We would have it'd be the T plus V for the system. So it has the potential energy, the first one, P1 squared over 2M1, plus you have the P2 squared over 2M2. I have all my kinetic energies together. And then what would I have? Then I have a 1/2 K1. I'll say, what does he? He's going to ultimately go to Q's. Does he actually have the intermediate things now? I'll just say R1 squared plus 1/2 K to R2 squared plus so on and so forth like this. Now, what can these K's become? If you have a K, how can you write a K? You can also write a K in terms of
The oscillation frequency.
the natural frequency of oscillation. Remember how that goes? It is omega squared.
Omega squared.
So this K here is going to be this omega 1. So I can do that with all, you can do this with all these things. Does that make sense? Okay. Now, is it made then the following assumption? Is that what can happen here? You can then take this energy here. So I'm just going to write it as a kinetic energy. Oh, I'll write it two separate terms. I can basically split this up into terms. These are going to be basically terms with large. Okay. Or they don't necessarily have to be large, but they're going to be something reasonable. The main thing is that we have another term here that these ones here. These are going to be the terms with a small. This is going to be small. Small. So what would that look like? If you had something with a large omega, what would that look like? It'd be something like, it'd be a potential like this. What would be a low omega?
One.
Something more like that. Okay. So what's going to happen here? This system here is going to write it like this. What about this one here? You're going to have these really, really big long oscillations. Okay. In terms of this, the words by Phillips, what do you think the modes like this are going to be connected with? These are going to be connected with floppy modes. So what he does here is he calculates basically the entropy of the system. He does it by the following way. So the first of all, what would be the degeneracy for the system here? And this is the part we can't do easily. Turns out there's a really subtle thing you have to do with the direct delta function. First of all, we haven't studied direct delta functions yet. That's going to be coming up next week. And we'll find out what about those are.
You know, we only have 2 more weeks.
Well, I know. We're going to get through all the X-ray stuff. I know that. I'm hoping to get through all the temperature dependent constraints, so either Monday or by Tuesday at the latest.
We're planning on scheduling any additional makeup classes for the other.
We'll have one additional makeup class. I think they're going to be okay. In other words, I can turn you free thinking it's okay. I mean, if there's still one big topic I'd like to do, but it's going to be okay.
All right, so how do we do degeneracy?
So what we're going to do is now this
Density of states.
calculates the classical partition, the classical number of degenerate states. And that makes sense because your energy is fixed. So it's basically when the energy is fixed here. So how do you calculate then the number of states? Well, what this is going to mean, does he call it omega? What do we call it? Hey, this one omega. So this is going to be omega. This is the number of states. He's going to basically, it's going to be the partition function with your without having basically your Boltzmann just Boltzmann. He's just going to count states. So he's going to basically do an integral over all the P1 values, integral over all the P2 values, all the way to the last one. And all the positions. And these at this point here, these positions he's now calling Q. The reason why comes from classical mechanics because that's what's called a generalized coordinate, or what's called a normal mode. If that means something to you, that's fine. If not, I'm just going to cheat go like this. And grow D3 or 2 all the way up to the last one. Here. And then if you remember, we have that weird factor here of this H through to the end. Now, you just can't do that because, and here's the complication, here's where it gets mathematically complicated. You just can't integrate over all position, all the momentum of all the particles, and all the positions of all the particles, because what? The energy has to be constrained to this. Okay, because we're saying that the energy is fixed, so this is fixed, and that puts a restriction on all these elements. Okay, and that's the part I'm just going to have to say what the result is. Okay, so with the restriction, that E is fixed. And given by that expression. Now, once you get that, how do you then find the
Wait,
entropy?
what's the result?
Well, I'm going to give you the entropy.
So you're saying that you'll give us the result. You just
I'm going to
Brush
give
it
you
off.
the entropy result. That's right. So once we get this, if I treat this as basically microcanonical ensemble, which effectively this is the system here has a fixed energy. And we're assuming it's isolated, so it is a microcanonical ensemble. If I take kb times the logarithm of this, that's going to be then my entropy. So since P is fixed, and the system is also assuming the volume is fixed as well. So it's isolated. The entropy is going to be kb ln of omega. In other words, S is the micro canonical entropy.
That's at that energy.
Because in microcanonical ensemble, the energy is always fixed.
So this is like an S as a function of T pretty much.
The T is not going to go.
But like what sets the energy of the system is effectively.
Yeah, so we're just saying the energy has some energy.
Yeah.
Okay. Now, when he does that, it turns out that you get two big pieces here. The S here has two pieces. Basically, a piece. This is going to be this part here. This is going to depend on large omega terms. Plus, he's going to have a term here that depends on the small omega terms. And I will, it has some weird notation. Um, I'll KB log of 4 pi of h bar n. This is the total number of particles. So it goes hn. Basically times the number of large mega terms. And he writes it in kind of a funny fashion. Times the product of all the 1 over, this is a product. Of 1 over the omega, 1 over the product of the large omega terms. Plus something that looks a lot like this, but not quite. So this is going to be 3NF KB log 4 pi E N H omega naught. Okay. This omega naught, this is going to be representative of the small omega. This is representative of this. Of the small omega terms. This F here, this is basically going to be the fraction of states with that small omega term. Fraction of small omega terms. Okay. That's what you got. So which of these terms is going to be larger? Which one's going to dominate?
Second one.
Yeah, this term here is going to dominate. Okay.
Or entropy.
These the important thing that we need.
How many floppy? Okay, sure. I can see
Okay.
why that's reasonable.
So what this says there is that S is dominated by the second term, which involves okay. So what we're going to say here is that our S here is going to be proportional to basically F. There's some stuff here, all of which is going to cancel. So what that means here is that when we go to our expression here that I just erased to the limit of Blackboard space and science, that when we go to here, this is going to be F, basically some reference compared to F. X. And there will be a temperature difference. I suppose the temperature difference. So this is going to be our main equation. So this is going to be the main equation. Oh, let's do one more other thing. What do we know about the number of degrees of freedom? I mean, what is it? It's going to be our 3n minus 6, because we don't care about that stuff, minus the number of constraints. Right? So if I divide this through by n, this is actually what's going to be, this is going to be our rule. What's that I'm going to go to?
0.
That's gonna go to 0. And this right here, we're just gonna call it sub C.
Action constraints.
Or how many, this is gonna be the number of floppy disks. So the n sub C is our constraints. Up here, so you do all this jazz up here. What's left over here? If the stuff is 0, what does it mean? Do we have, what do you call our system? Isostatic. If this is negative, rigid. Okay. If this is positive, floppy. Okay. So what we're going to do, we're going to then figure out from the model of our glasses how to calculate this for different systems. And there's a, you have to know a lot about the structure to be able to count. And there's going to be, when we look at the board, we're going to start off with the first system that was done historically, which is this germanium selenide glasses. That's going to be kind of more straightforward what to do with it. There's a little bit of an art form when it comes to the alkali borate glasses. It's going to be rigorous, but it's going to be, you have to be careful how you count. Okay. So our main equation is this. And the only way you can actually understand this is you actually have to. So we're going to do examples. So our main equation is going to be this guy. This 3. I'll always calculate 3 for you. So when you get to this equation, I will always provide 3.
Nice.
Because I like to help out. Okay. Minus NC is R. This 3 minus NC. This is our main equation.
And those NCs are at TGs. Over
These are all at TGs. I didn't put that in here just for that. Okay. These are going to be evaluated to corresponding T's. They just start with. Okay. So that said, actually, let's apply this. So let's apply this. To very first paper on topological constraint line, which is to a system of germanium selenide glasses. And this will also give us an example to talk about these glasses. They have kind of an interesting structure. So what these glasses, the GE SE glasses are written as they're written in really kind of a funny form. It's GEX SE1-6. That's how they're always written.
what's funny about that?
I guess I like things here, not X. X there. That's fine. So what would happen if my X is small? What would I have a lot of? Slowing the air. And these are going to be a good glass former over a wide range of X values. So these glasses form glass over wide range of X values. Particular instance. That's a reasonable range.
Not that wide.
Like I have. Everyone says it's a wide range. They quote this here, and fine. Okay, it's good enough. So the question is, what happens here? It turns out there's actually kind of a novel structure that happens here. So let's look at two cases here, because you need to know something about what this glass structure looks like if you can't figure it out. Okay. So let's look at at GEX SE1 minus X for 2x values. The first is going to be x equals a third. The second is going to be x equals 2/5. I think that's fair.
Also, like a glass formation range, such a, like, it has to be a function of what trade, laboratory pressure. Okay.
I mean, you don't, without having a fluctuate, you don't have glass. You always have to specify the wide strength.
Mhm.
But evidently, these things are actually from a glass over a wide range of stuff. And my response to that was, it was quite profound response. Okay, does 1 minus a third have a better name?
2/3.
2/3.
Identical.
Okay. Okay, so we're going to do our little thing that who knows whether it's going to be correct or not. We're going to multiply 3 by 3, and this gives us GE SE2. Hey, what does that look like? SiO2. And this is going to look exactly like SiO2. So this right here, this is basically, this is in the same column of the periodic table as silicon. And selenium is in the same table as oxygen. So what that looks like can then answer the problem. So you don't have that problem. Regular tetrahedron.
But the covalency of those bonds are much higher than silicon, right?
Sure.
What is the valence shell of germanium and selenium?
It has to be something similar to octave. They're in the same column. And if they're in the same column, then that first part of the periodic table is going to be the same. And also, you're going to work that out as otherwise. Okay, now let's do the same thing then for G. Also, let's talk about this. So if I'm in this range here, what then happens here? If I'm here, the glass is just a whole bunch of these tetrahedra connected together. But what happens if my X gets smaller? I have more and more selenium. So what are the glasses going to look like here? They're basically going to be this with a whole bunch of selenium. And what John actually did his PhD in is actually came up with good chalcogenic potentials. And it turns out that if you use good chalcogenic potentials, you actually recover the experimental results. It turns out that pure selenium glass makes very long chains. Okay, so realistic potentials.
Yeah, so very strong.
Okay, and data.
I can see
Experimental
those two words together.
Are both consistent in showing that SE glasses form long chains. So in other words, what you do is you basically have this SE connected to S. You get things like that. They form long chains. And data and the models are both.
Cross linkage at all or no?
The person would be no, or if there is some, it's actually quite little.
Okay, but there's like entanglement of these
Oh,
chains.
there have to be a thing. That's what we did wrong.
Yeah, I understand.
Like that. So that's what this looks like. So if I'm in this range here, in between here, if I'm not here, this would be, here are these guys here. X equaling 0, that would be this guy over here. What do you get in between? Basically, these with basically long chains in between. So you're gonna get classes that look like this. So this is in this compositional range. Things like that.
Oh, and you can pull the like average length of the chains by concentration variation.
Okay. So that's what you get here. So now let's look at the range of what happens when you go from a third to basically 2/5. So let's put in the 2/5. Now let's look at, and again, without the structure of how this looks, you can't do these calculations. So this technique here, you just can't willy-nilly apply. You can't look at a family of glasses without knowing the structure and coming up with the how the TG varies with composition. You have to know something about the structure.
Hopefully a lot of stuff. Like if you're missing out on a particular structural phenomenon.
It's going to fall apart. Yeah, well, if that structural phenomenon is large. So look at X equals 2/5. Okay, so now we get GE 2 SE 1 minus 2/5. Okay, 1 minus 2/5 is what? 3/5.
I'm so glad I can do fractions.
Fraction, good. All right. Okay. This is GE2 SE3. Oh, these look like these are a little more fun. What this looks like is the following. So get this tetrahedron, get a tetrahedron here. Well,
So
it shouldn't really draw it because it should be more like a pyramid here. It's more of a. Oh, that's actually confusing. I just said. That's the structure you got.
like
Yeah,
that.
with.
Okay.
Okay. So you get.
You can make it into a problem.
You're getting that. So
All right.
for my fist would be the GEM.
Okay.
Okay.
General Electric's involved in that?
Okay, so that makes sense. Now the question is, what then happens between these two here? So if you're in the range here, if you're in this range here, for the most part, what you do, you have a combination of these guys, and then a combination of these guys over here. Now the question is how much of each. So we get to do some more. So let's look at these two things, and again, we need this before we.
Are there any ideas of why that doesn't happen in silicates or germanium oxide glass?
There probably is. I don't know.
Okay.
My guess is that the GE is occurring later. Yeah, silica, the germanium, I think.
There's a I don't remember.
But usually the further down you go here, you get your rules start getting more funky. And so it's gonna be some funky rule.
Okay.
I hope that's not too technical, the chemistry window there. So the question is, we're gonna have this guy here. This is in this compositional range here. This is gonna form basically, I don't know. It's gonna form some of this guy. Give me a certain amount of this, I'll call that A. And then a certain amount of this guy here. I'll call this B. And the question is, what are A, what are B? Okay. Now we get to count more. Okay, there's a reason we spent time on counting. So on this side here, how many germanium do we have? X. On this side here, how many germanium do we have?
A plus 2B.
A plus
2.
2B. And I'll do the same thing then for selenium. On this side here, so this is, if you look at G, if you look at SC. On this side here, how much selenium?
100.
1 minus X. For this term here, what do we have? 2A. For this term over here,
2B.
plus 3B. Okay. Call this equation 1, this equation 2. I'm going to multiply equation 1 by 2 and subtract equation 3. So I'm going to say 2 times 1 minus 2. Okay. If I do that, so if we do that, what do we get? We get 2x equals 2b plus 4b. We're going to subtract from that. 1 minus x equals 2a. 3b. The 2a's go out, so this side here gives me 2x minus x plus 1 equals then b. This tells me that b equals.
You're saying and writing different things, but it's okay.
I-
Writing is correct, yes.
Usually go with my writing, except if they're both wrong,
Yeah.
then then both.
I just heard you say
Okay.
something wrong.
Oh, but you're used to me. I think
Yeah.
after a while, everyone gets used to me.
But writing's correct.
Okay. You speed, not proving you speed. Okay, 3x minus 1. Does that make sense?
Yes, man.
Now, then what does that mean then about our A? I'm going to put this in, and over here. So this is going to tell me then sub into 1. We sub into 1, what do we get? We get x equals A plus 2 times 3x minus 1. And this is A plus 6x minus 2. And this is A equals x minus 6x plus 2, or 2 minus 5x. What I could say mid-range here. We have this. Like that.
Yeah. Curious how we arrived at that. Like, keep going.
Now let's do the other range. So what do we say we have here? When I write this guy here. Now, at least let me get this before we head out. And so we said this is 2 terms. In this range, what do we form? For x equals a third, we get this pure tetrahedral structure here. So I'm going to say I have A of that. And then what else do we have? If not there, we have selenium chains. Hey, can we solve this?
Yeah.
Yes. Okay. Let's do the number of germanium on this side. On this side, X. On this side, A. Okay, I think we're done. Okay. What was that? Okay, so remember being something more. I thought there was a 3 commands. Okay, let's do the SE then. On this side, 1 minus X equals, on this side, 2A plus B. Hey, I think we know what X is. Let's substitute it in here, because this is X equals A. Crazy. So this is 1 minus X equals 2 times X plus B. Okay, oh, there's my 3. Good, okay. So this gives me 1 minus 3X equals B. So what do we have for this? Then you get this guy. This guy here. That's in this convolutional range. So now we have to start counting bounds, and we'll start that on Monday, but let's just go, counting constraints. So what are we going to have here? What kind of constraints could we have? Angular constraints. And so we're going to have to figure out how many angular constraints we have. What else can we have?
Linear constraint.
Linear bond constraints. And if we have these long tails of these selenium, what else can we have? Maybe some sort of van der Waals constraint. Now, maybe some of these are important, maybe they're not. We don't know. But what we're going to do is we're going to say that as we lower the temperature, certain ones of those bonds are going to come in at a certain time. So we're going to start off with a high temperature. At a high temperature, how many constraints do we have? None. We're going to start lowering the temperature, and then what happens? Either the linear bonds come in or the angular bonds come in, probably being the first. And the only way you can know that is basically you have to have some sort of an experimental insight. It turns out in this case here, it turns out that the angular bonds are going to come in first. So the angular data, probably from NMR. So that's we need Ben here. Dude, look, easily agree with me that the NMR data clearly show that for these systems, the angular bond kicks in. They're going to lower the temperature, and then the linear bonds. Now, sometimes you have to be a little careful because you can ask, what kind of angular bonds do we have? Is it an SE-GE-SE bond? Or is it SE-SE-SE bond? Or who knows what? So we're going to maybe have to have different constraints depending on the bond. Okay? Have a good weekend.